Hey guys, how are you doing? This is JSer. Today, let's continue our journey of LeetCode. This is 139 word break. We're given a non-empty string and a dictionary word dict containing a list of non-empty words. Determine if S can be segmented into space-separated sequence of one or more dictionary words. The same word in the dictionary may be reused multiple times. Okay, we can assume the dictionary does not contain duplicate words like LeetCode, of course, it matches, and apple, pen, apple, apple, pen, apple. So it is true. Well, I think the naive solution will be very obvious. We just follow what we are told to. We first try to match a word at the beginning. If like say leet, okay, we match leet, and then we can start from here to see if any of the words matches and go to the next one, right? And we do this over and over again until we meet the end. That's the end of our solution. So if we failed, and we can go to the next word, right? So for each round, we have all the options from this word dict. And yeah, that's a typical like a backtracking. And it's like a tree. We go to the left node and to the end, and we fail, we just go to the siblings, right? So it's backtracking, and it's implemented into recursion. Let's create a walk method called, okay, this is naive backtracking. So we create a walk method. The parameter is simple. It's a start index. And finally, we will walk 0, and we return the result. So this method returns if we could go down to last digit, last word character from index I, right? Cool. So what do we do? Well, for each index, we will pick a word, right? For let word of word dict, we'll try to see if it matches. So the length, and we see if s slice I a length, right? Length, if it is 1, then itself, so I plus length, if equals to word, if it is so word, then yeah, it is matched, right? If it is not, we go to the next one. Whether we could return, no, we need to continue check the next one. So we should start walk from I plus length, and we should return it. No, because if this doesn't match, we can go to next word. So we need to keep the flag let is matched, false, const matched, if next matched, if like this, and if next matched, if next one is matched, I can say it's sure, we should say it's return true, right? If not, we will continue our for loop here, and then finally we will return is matched. Or to make this better, I think easier to understand, I think we should just set this to true and break, right? Cool. And when will this recursion end? Well, surely for a valid input, we will match the last word, right? Code here, and I will be moved to over surpassing the last index. So if I is bigger than s.length minus 1, we return true. Cool. Let's try run the code. Cool. Let's submit. This is naive backtracking. Well, you see, we got the TLE, Let's analyze the time and space complexity. So we're given an input like this. You see all A except the last one, and then there's a. So all the substrings of same character except the last one. So if we take a look at our walk method, you will see that all of these four will be fully matched, right? Generally, for except the last one. So these will be worst case. Worst cases, let's see. We walk from 0, and we will be providing with all the possible next index, right? So next one was 1, next one from here, next one from here. So if it is matched, of course it matches for worst cases, and we will walk them again. So actually, it's we will start a slightly shorter string, but check against the length. So for our solution here, we're looping through the word, right? So actually, this is not good. This actually for time would be, let's see. There will be, for each position, there will be n possible with n checks, right? So t n, the time of starting from I, which is the length of the string, would be t the time of the next one, right? T n minus 1 compared to the next one, plus if the second matches, well is t n minus 1. It means all these words are matched, right? If the word is longer than the string, well, if it's longer than it, we still will check it, right? So this actually will be tn minus 1, tn minus 2 plus tn minus 3 until what is it? It will be t minus, say the length is m and n and m, n minus m, right? This is the worst case. Well, when it is minus, there's nothing to check. If it's and t for k will be equal to constant, I think. So it's constant for k is smaller than equal to 0, right? T1, if there's only 1, it will be k. Obviously, for the k, for the minus ones, it will be in a complexity notation, it could be omitted, right? So I think this should be t plus minus 1 plus t minus 2 plus t1, right? Plus this, I don't know, it should be c. And then this actually will be 2t n minus 1. So the time would be 2 to the power of n. space. Space, actually, we don't use any extra space, but the cost stack, right? Cost stack worst is O linear. Cool, but it's TLE, so we need to improve it. How could we improve it? Well, when we use recursion, we always want to do memoization. Suppose this worst case, we check A and A again, A again. So for each index is actually traversed already, right? From the notation here, if we can match, if we can go A here, we don't need to start. If the case of all A doesn't satisfy our needs, for AA, we don't need to start from here, right? We can directly start from here to check. So the strings before is actually already traversed, so we can use cache. Let's use memoization. The I means we could go down to last character from I. And I start with nth. Yeah, if we, let's say, if the last I words cannot go to there, we could omit that. So generally, it's a memoization of this walk method. So we create a cache, new map. If cache has I, return cache get I. And yeah, cache set I is matched. Cool. Let's try run the code again. It should work. Submit. You see, we're much faster than the original one because we avoided an unnecessary calculation. Let's analyze the time and space complexity. Space, obviously we use an extra the cache for each index. The index will be 0 from to the length of this string, so it's linear space plus the call stack. Well, it's linear too, so total it's linear time on linear space. About the time is a little different, I think. Where there's let's see, the words submit is like this, right? So what we have is for I, which means either we could match from I to the n, right? How many cases are there? There are n cases, right? The only n cases we cache. And when we're checking that, for each index, we're checking, like from index here, we always loop through all the words and check it against the cache, right? So there will be n possibilities times n indexes. Well, here we actually see that we could improve this method a little bit. Suppose there are a lot of dictionary. If say there's a very long word in this dictionary, we start I. We should choose the shortest word in this string rather than a dictionary, right? Well, that's another topic I'll explain later. So currently, for this one, it should be n to the square. So actually, we're doing great. Now, if you have done the memoization, we'll naturally deduct another solution, which is called dynamic programming, right? We could avoid the recursion thing. So let's analyze our problem a little further. Here we actually already got the key caching, the key point to cache. It's the index, right? So for each index, well, we could determine if we can get this index, right, from 0. So for the first letter, we matched, like said we can. Okay, now let's go to the next one. If we can or not. Well, that depends on the previous one, right? We can say the okay. Let's start from here. If we say we want to check if we can match the whole word from 0, we only need to check each word of the word dict matches the word the substring from the index and backward for the length. AA if matches, and the string left is actually already calculated in our cache. So for these, we could do actually the same as the here with the memoization, but we could avoid the call stack, so it will be a little better. Let's try to do that. So we write it into dynamic programming. Of course, now the result becomes const result, not result, but dp. Now it's pp can walk to. Can match at. All right, so it's an array, obviously. Now I remove this. So the result would be return can match at the last one, right? So this is like this. And we will loop through all the possible index. And what we will do, we will, yeah, as we did before, we'll loop through all the word in the dictionary and check it backwards. For that word of word dict, const length would be word.length. And const the pref matched. If the previous space is matched, so we could get the results from the canmatch at, right? But it might be overflow. It might be smaller than 0. For that case, will be true. So the pref index would be, if length is 1, it's itself, right? So the end of previous match would be I minus length. If it's smaller than 0, then it's true. If not, there should be a cache of itself, I minus length. So what we do, we will check all the possible words, right? So as we did before, we have is matched or not. Default, it's false. And if previous one is matched and the word matched, the new word would be as slice the I minus length plus 1, right? And I plus 1, if it's equal to word, if it matched, then we say is matched equals true, and we break, right? And we could say for match I equals to is matched. Cool. I think this should work, right? Let's run the code. Uh-oh, there is a can match at is not a function. Function? Can match at is not a function. Oh, it's array. Sorry. False? What? Okay, can match at I is from all the index. Cool. Is matched for word of work dict. Length is word length. Pref match is I minus length. That's true. It's right. Can match at length. Cool. And then is pref matched. Okay, slice I minus n length. Why here -1? So here is the problem. It should be a +1. My bad. Cool. Yeah, let's submit. Okay, it's a little faster, but it doesn't matter because the time complexity here is actually, you see, for each index, the worst case is that all the word dict is traversed, right, to get the result. So it's actually O n times the word dict length, the worst case. So it's S, let's say M, time space. We use an extra space like linear time, so it's O n. As we said before, actually, this O n thing will depends on the word dict, but it's very, very, if there's a lot of word, it's actually, let's see, if there's a lot of word, actually it's a waste of time, right? We check for every possible solutions with the length, so we can actually improve this. If we do it based on the input string, there is maximum n possibilities, but if we use word, it's actually it's depending on the length of the word dict. So actually we could improve this a little bit. This is called slightly improved DP. The idea is that we avoid traverse through the word dict, right? The basic idea is the same, but this is a word. Okay, word break. Let's say this is word break 1, and we will create another one. Two. So the second one is based on the S, not for loop of the word dict. So if we do that, we could use a hash map. So we get the substring from the input S and check directly if the word dict is exists or not, right? So we say there's a dict map new set word dict. For S, match true. So now it's not for word of word dict. It's for let k equals 0, k equals I, k is bigger 0, k minus minus. Okay. We go backward, and so the word would be as slice k I plus 1. The proof match is the same. Wow, this is simpler. Proof match would be k minus 1. K minus 1. If canmatch is k minus 1, this will move the for loop, and so it's if it is proof matched, and this dict map has, right, has word, then it's matched true. If not, it's true and break. And finally, we will check if we could set it's to matched. So this should also work. Let's try running it. Let's first comment this out. Yeah, okay. This is slightly improved DP. This deep B based on S. This is deep B based on with searching on word dict. It's deep B with substring from S. So which one is better? This is. I think we could. This break 2. Okay. Actually, we could. This is the same. We could say this is work 1, this is work 2, and we can merge these two. Which is the smaller one. I don't know whether it helps or not, but maybe not that. Okay, let's first analyze the time and the space complexity of this one. Time, of course, it's for each one index n, and because we're using a substring, it's n square, right? So it's different than the previous one. Previous one is nm. Space, we use this n and use a map, so it's n plus m, right? Cool. Now, actually, we could use this both, like we create a real one. Choose above one based on input. I'll say if word dict length is smaller than s.length, we use this one, word break 1 as word dict. If not, we use word break 2. It is right? I don't know. Anyway, I'll try. This should also work. Return. Oh, sorry, I forgot to return. Okay, return. Yeah, submit. Not that fast. So maybe it is faster, but there's not so much difference. Okay, so in this problem, we use the four 1, 2, 3, 4 approaches. Basically, there are 3. First one is recursion with backtracking. This is some naive solutions that is easy to come up with, and we've done the recursion, so naturally we can use memoization to improve it. And after if we've finished the memoization, we could use the dynamic programming to avoid the deep call frames. Yeah, so that's all for this problem. Hope it helps. See you next time. Bye bye.